Okay, let's start. So today we are going to do 12.9, which is on analysis of dependent motion. This is where we'll be talking about system of pulleys and masses attached together, and how do we analyze those kinds of systems. Okay, I'll just illustrate this with an example. A really simple example. And sort of we'll develop sort of the intuition of how to solve these problems, and this is very simple. You don't need the tools I'm going to show you in this particular example, but later on when we do more complicated examples, you'll see that what we get from this example can be applied, and it'll really be very helpful. So if there are two masses connected by an inextensible string, okay, what that means is that the string doesn't stretch. Let's call this mass A, let's call this mass B. And if I ask you that, if I tell you that if mass B moves with velocity VB, then the velocity of mass A is what? If you move B with velocity VB, what's the velocity of mass A? It's the same, right? VA is VB. You don't require to do any math or anything like that, just figure this out. However, the methodology we'll use to solve this problem is what I'm going to describe next, and you'll see that's going to be more useful when we do more complicated examples. What I'll do is I will randomly fix an origin. I will indicate this distance. So this is origin, means that this is where I measure distances relative to. Let's call this distance as XA. This distance is XB. And this L is really the length of the string plus half the width of block A and B. Okay, but that length pretty much doesn't change with time, right? L is constant. It's constant because the string is inextensible. If it was not extensible, then you would see that L will change as a function of time. Okay, if L is a constant, then L dot or dl dt is 0. So I fix the origin, I assume distances A and B. What I'll try to do is I try to find a relation between the motion of B and A in terms of XA and XB. And from that figure you can see that XB is XA plus L, right? Just from looking at that figure. So once you write that expression, then what you do is take the derivative of the whole expression with respect to time. With respect to time gives me dxb dt equals dxa dt plus dl dt. But since L is not a function of time, that is, L is a constant, dl dt is 0, which means that dx b dt, which is vb, is equal to va. So we got the same thing, but by using this recipe, which is fix the origin, right lengths of points of interest, which is in this case a and b, and then take the derivative. Obviously, I did not require, you wouldn't need to do all these things, but you see that we can take the same thing, those 3 steps, fix the origin, assume distances, and then find relation, can be applied to more complicated problems. So what I'll do is I'll do a more complicated problem using the same recipe, and you'll see that turns out to be much easier to analyze if you know how to do this. So before I get to the recipe, let me first solve another problem. And this is, I would say, in the fringe of being intuitive and non-intuitive. For some, it will be very obvious, but some it may not be that obvious. Okay, so this is a setup consisting of 2 pulleys, as you can see, and there are masses attached, A and B. Okay, and so let's assume that we are given a sample. Given, so let the velocity of A, B, VA, and let's assume that it is downward. Right, it's moving down. So you're pulling A downwards with the velocity of A. Okay, so far there's no gravity, nothing. We're just looking at motion where there are no forces. So don't get confused. There's no F equals ma, nothing. It's only kinematics, which is motion of bodies. Find the velocity of B. So we want to relate the velocity of B to the velocity of A when we are given the velocity of A. Okay, so this is, I'm just going to, I'm going to draw the origin on a different figure just so that I'm very clear. So the same recipe, fix an origin. Okay, in this case, makes sense to fix the origin to, motion is in the y direction, so I'm going to fix the origin here. So this is my origin. Then draw distances to points of interest. In this case, I'm interested in the motion of A and the motion of B. So let's say this is YB, this is YA. Okay, and remember in the previous example I drew the length of the string, right? That was a part of the getting the equation. So in this case there's a single string which is wrapped, well, there are two strings, right? There's one here, there's another one there. So you could, if you want, draw this. So this is L1. What else? When I want to find relation between y and yb, I want to eventually find in terms of the length of the string which is wrapped around, which is usually this, right? So I'm going to somehow come to the point where I can say that the length of the string, which is the red thing I just showed you, is constant, doesn't change with time, right? The string is inextensible, the cable is inextensible. So if I can find the length of the string which is wrapped around, then I should be able to use that to take the derivative and then get the expression. So one, I chose the origin. Second, I would find the length of a string. Let's say that is L. So L, in this case, is the red thing which I just drew, and I would try to write it in terms of YA and YB and L1. So that string consists of, well, this part. It consists of this part, this part, this part, and this part. So this part right here is what? It's YA minus L1, right? This part, first part, is YA minus L1. If the radius of this pulley is R1, then this part of the string would be, what's the length of the string which is wound around the pulley? It's almost half the circle, right? Half the circumference of the circle. So it's pi times R1. Okay, then I need to move on to this part. Okay, to get this part, looks like I also need to write this length, which is L2. So it's going to be YB. No, sorry. This part is going to be YA minus L1, which is this distance, minus L2. So YA minus L1 plus, minus L2. Do you see how that comes? This is because of this distance minus this is this. Yeah.
Why is it pi r squared?
Why isn't it pi r square? Pi r square is the area of the half circle. The circumference is 2 pi r, right? The full circumference is 2 pi r. So half of that is pi r.
So how do you know yours will pi?
Just from the figure, this figure is poorly drawn, but you see that it's more or less half goes over half. It goes from there to there. It's a poorly drawn figure, but you can make that assumption. I want to give you a better drawn figure if that's the question. Yeah.
So pi r is the length of the curve.
Pi r is the length of the half the circumference, right?
Yeah.
So what's the circumference? It's 2 pi r, right? So what I need is half of this, just pi r. So you'll see that you don't quite need pi r. I just wrote it down so that it's more complete. But when you start solving problems, you'll not really care about pi r. You will not really write pi r. But just to be very complete, I just wrote pi r there. So this is this part. Then we have this string. Let's assume that this length this circumference, well, this radius is r2, so pi r2 gives me this string. And then finally, I need to write length of this string right here, right? It's going to be yb minus L2. So what I did was I wrote the length of the string which wraps around both the pulleys. Okay? Is that okay? Do you see how I got this? So step at a time, just go length at a time. Okay, so then use the same idea we used earlier, which is once you have an expression relating the variables of interest, then you take the derivative with respect to time. So L dot is ya dot minus the derivative of L1. L1 is this length. Okay, that's not going to change with time, so that's 0. So let me write that down to be complete, and then we can factor it off. Plus pi r1 dot. The radius of the pulley is not going to change. That's 0. Plus ya dot minus L1 dot minus L2 dot. Again, L1 won't change with respect to time. L2 will not change with respect to time. And then there is pi r2 dot. The radius of the second pulley will not change with time. And then yb dot minus L2 dot. Again, L2 will not change with time. Also, the length of the string, which goes over two pulleys, will not change with time because the string is extensible. In general, in such problems, all the string lengths are going to be inextensible. So this is 0. So we're left with 0 equals ya, well, there's ya dot here and ya dot over here. So it's going to be 2 ya dot plus yb dot. Okay. Ya dot is nothing but the velocity of point A, so VA plus VB, and so VB is minus 2VA. Which is telling two things. One is that the motion of or the velocity of B is twice that of A. And the second thing is direction of velocity of B or direction of motion of B is opposite to that of A. So this is indicated by the negative sign. Right? So the second thing is obvious. If you move B down, A would move up. That's given by the sign. What may not be very obvious is the factor 2. Okay? The factor 2 comes because you have basically you can see the pulley which connects A. There are two strings which go opposite. That's why you get the factor 2. Okay, that is, when you move B by unit distance down, or when you lengthen the string on B by a unit distance, you'll see that half of that distance goes to move the right side of the pulley connecting A, and half goes to the left side. That's why you get the factor 2. Okay, but You could do it intuitively by looking at the figure, which I don't know if that's how. Have you done these kinds of problems before? Perhaps in high school or something? No?
Physics one.
Physics 1? Okay. Did you use something like this, or you use the argument? Use something like this? Okay. So, well, this I think is a much easier way to do it. The chances of you messing up signs and magnitudes are lower if you follow this recipe. That is, you fix the origin, right distances, and then find a formula and differentiate with respect to time. Okay. Now, in this case, again, there's some things you do not have to do, which is you do not have to write R1, R2, L1, L2. Okay. You do not have to do that. In fact, what you can do is, in this case, you can fix the origin here. You fix the origin, L2 disappears, and instead of specifying YA as the distance from the origin right to here, you can just specify YA to be the distance from here all the way to here. Because the motion of this point on the pulley and the motion of A is the same. Right? So we'll basically see in the next few problems, we'll try to simplify this as much as possible so you're not writing this big an expression. We'll sort of bring it down to only terms we care about. This has become obvious when I solve problems. Okay, so this is the recipe. Do not, well, there's no time to write for this because I'm going to go through problems. But essentially the same thing which I told you. I used all the machinery I used to solve that problem is right here. Choose a datum line, should be a datum line. Okay, that's the origin. The next step is assume variables that describe the motion of points. So in this case, in the previous example, we said YA, YB, or previous to that was XA, XB. Okay, assume suitable also constant variables. Okay, so in this case, it means choosing things like lengths of strings and radius of pulley. You don't need to do the radius of pulley, but sometimes you have to do lengths of strings, and there'll be some problems where we do that. Then find the total length of the cable, which we did, right? L equals all that big expression on the right. And then differentiate once to get relation between velocities. Okay, sometimes you're told to find velocities, sometimes you're told to find acceleration, in which case you need to differentiate twice. So if I told you in the previous problem, instead of saying velocity of B, I gave you acceleration of B, then you'll have to differentiate once more to get acceleration. So again, I'll post this, you do not have to copy it, but essentially you just keep doing the same thing on different problems and you'll see that you can solve this problem without having to intuitively think of how to solve it. So first question. Okay, let's read it. So if the end if the end A of the cable, so that's A, it's moved down with a speed of 2 meters per second, determine the speed at which the block B rises. Okay. So unlike the previous problem, there are 3 pulleys now. So I'm going to use the same recipe, the same thing I did in the previous problem, except that now I'm going to try to not write radius of the pulley because that's not going to be, that doesn't really help us because that eventually differentiates to 0. So in this case, I'm going to choose the origin to be here, and the only reason I'm choosing the origin right here is because this length here of this cable will not change with time, right? This is a constant. So I won't gain much by moving the origin to this point. Okay, so that's why I chose the origin to be here. The next step is to find points of interest. So in this case, the points of interest are A and B. You're told to find velocity of A as a function of velocity of B. So let's call this YA, and this is YB. So I could potentially choose this as YB, but why should I do that when I know that motion of this point is the same as motion of this point, right? Because this thing here is inextensible. So I'm not going to draw it all over there, but I'm going to draw it right here, YB. Okay, I could draw it right down. All I need to do is I need to put in a length L, but that length is a constant, it doesn't change with time. So I'm better off just choosing the origin to be, well, the distance to be right till the previous, this pulley. Okay, now we have to define in that algorithm I showed you, there's the third step is to define intermediate variables. Okay, it could be lengths of strings which are constant, it could be other things. In this case, what I think I would need is I need to describe the motion of C, because when I try to find the length of the cable, C will invariably show up. That is, I'm going to choose this as another intermediate variable which will help me to solve the problem. Okay, sometimes it's not obvious. In this case, you should just proceed to go to the next step, and then you can backtrack and then try to write YC. Now, here's something which you want to realize is in this problem is that there are two strings involved which are going to move when A moves down. There's one which is wrapped like this, and there's another one which is wrapped like that. So in general, if you see that when you move this mass, if this string is, well, the length of the string is constant, but these lengths will change, and so will these lengths change. That means that you need to write two expressions as opposed to one expression I wrote for the previous problem. In the previous problem, there was just one cable wrapping around, right? There was this one and that one, but that just stayed constant. Well, it was not really changing length. Here, this and that will change, but there was only one string. So I've written one expression. Now, in the second problem, which I'm doing, I have two cables. So I have to write two expressions. And that's where you'll see that that's where YC will come. And it will basically help me to eliminate YC from the two equations. So let me do this, and maybe it'll be obvious to you why I wrote YC. So the first thing I want to do is write length of this cable, let's say. Okay. So, and I want to write it only in terms of the variables I've defined so far, which is YA, YB, and YC. Let me try to do that. If I'm not successful, then I might have to introduce more variables. So let's find this distance. It is simply YA. Okay, before that, let me first write here L, A, T, C to integrate that this is the length, this is the length, this length. Okay, A, D, C equals YA, which is this part. Then I need to write this part. What's that part? What is the length of this part? It's YC. Okay, now one thing, what happens many times is that people observe that this point A and C is the same height, and they do not write YC, but they write YA. That's incorrect. So don't write this as YA plus YA. That's not right. It's YC. It just happens at this instant of time, C and A are at the same height, but eventually when time moves on, well, you see that C goes down and A moves up. So do not write, don't make the mistake of writing that as YA. Finally, I need to write length of this part, which is what? What's this length? Yeah, it is YC. So let's differentiate this. differentiate with respect to time. So LADC dot equals YA dot plus 2YC dot. L dot is 0. So this is how the motion of A and C are related. Okay. Now that's not going to help me solve the problem. Well, this is not the final answer because I only know the motion of, I want to find the relation between motion of B and A. So that has C and A. So that's where I need to write the second equation, which depends on the other string, this one. Hopefully when I write this expression, I'll have something between A, B, and C, and then I can eliminate. Okay, so then let me call this A, B, let me call this point, let's say E. So L, A, B, E is the other string. Okay, so I need to find this distance. What's that distance? What's this distance? It's YB minus YC, that's right. YB minus YC, right? So YB minus YC. Okay, then the final thing I need to do is write this length. What's this length? It's just YB.
So anything above the origin is a constant?
Yeah, it is constant. Right? It doesn't change with time. That part of the string will not change. You could write that as L1 or L2, whatever you want, but the derivative is what we're interested in, that's going to be 0. Okay, so let's differentiate with respect to time. So I end up getting 0. Let me write it as L dot A B E equals 2YB dot minus YC dot, but L dot is 0. So now I have, that's my first expression, this is my second expression. I have one relating A and C and another one relating B and C. All I got to do is eliminate C, Y dot C. So if you put 1 and 2, you get 2Y dot B is equal to Y dot C equals minus so I got this from 2, I got this from 1, so 2y y dot b is equal to minus y dot a divided by 4. That's this expression. And so since y dot a is 2, y dot b is negative 0.5. The key thing is that velocity of B, okay, the velocity of point B is 1/4 of the velocity of A, and that happens because of the two pulleys. So what happens is there's demagnification, so to say, magnification of motion. In this case, the motion doesn't get amplified, but it gets de-amplified by a factor of 4. So if you move A by with the speed of 2 meters, you only get a quarter of the speed at A. Right? And then the sign tells you about the direction, which it says basically that if A is moved down, then B would move up, which makes intuitive sense. Right? So if you get all the signs right, then your answer